Is it possible time travel? Time travel, while a common concept in science fiction works, is not practically possible according to our current scientific understanding. However, the concept of time travel continues to captivate both the scientific community and popular culture. Here are some fundamental insights into time travel. Time machines and theories. Time travel has been explored through various theories and approaches. In some science fiction works, time machines are used to travel through time, whereas in physics, Einstein's theory of relativity explains the flexibility of time and its relation to space. According to the special theory of relativity, when an object travels at very high speeds, it can affect how time flows. Paradoxes. One of the most famous aspects of time travel is the paradoxes that could arise when traveling back in time. The grandfather paradox. Let's imagine you have a time machine. You've gone back in time, and you killed your grandfather. The grandfather paradox raises the question of what would happen if someone traveled back in time and prevented their own grandparents from meeting. How would that affect their own existence? Such questions highlight the complexities of time travel. Scientific challenges. Physicists generally consider the practical development of a time machine or a method to rewind time to be impossible based on current scientific knowledge. Time travel poses numerous physical and theoretical challenges. Theoretical studies. Some theories suggest that under certain conditions, time can be bent or that it can flow at different rates. However, these theories have not translated into practical applications. Time travel in popular culture. The concept of time travel has been a central theme in many science fiction novels, films, and TV series. For instance, H.G. Wells' novel, The Time Machine, and the Back to the Future film series explore this topic. Black holes and gravity. Black holes and gravity represent two significant physical phenomena where time and space are affected in intriguing ways. Here's more information on these subjects. Black holes. Black holes are regions where gravity is so strong that they warp the surrounding space. This warping, predicted and confirmed by Albert Einstein's general theory of relativity, is caused by the extreme gravitational pull of massive objects. Black holes are so massive that not even light can escape their grasp, making them effectively invisible. This phenomenon is due to the existence of an event horizon, a boundary beyond which nothing can return. There is substantial observational evidence supporting the existence of black holes, helping astronomers gain a better understanding of the universe. Gravity and time dilation.
I bet.
Well, every hour we spend on that planet will be 7 years back on Earth. That's relativity, folks.
Gravity influences the flow of time. This is a phenomenon known as time dilation, as described by Albert Einstein's theory of relativity. In regions with strong gravitational effects, time passes more slowly than in areas with weaker gravity. For example, time on the surface of a massive planet or star passes more slowly than it does for an observer in space or on a planet with weaker gravity. While these effects are not noticeable in our daily lives, they become significant under extreme conditions. Technologies like GPS Global Positioning System account for these differences in gravitational time dilation. Satellite clocks must be adjusted to compensate for the effects of gravity to ensure accurate global positioning. These concepts are based on fundamental principles that help us gain a deeper understanding of the universe. Black holes and gravity's time dilation illustrate the complexity and diversity of our universe. When we look at stars, we are actually seeing their past states because light has a finite speed, and it takes time for light from stars to reach us. Here are some key points. The speed of light. Light travels at an extremely high speed and covers approximately 299,792,458 meters per second, or roughly 186,282 miles per second in a vacuum. This speed is one of the fastest known in the universe. Distance to stars and galaxies. Stars and galaxies are measured in terms of their distance, and these distances are linked to the speed of light. In other words, to calculate the distance to a star or galaxy, we consider how long it takes for light to travel that distance. Seeing the past. For instance, the light emitted by a nearby star may take several years or even decades to reach us, depending on the star's distance. This means that when we observe that star, we are not seeing its current state, but rather its past state. For more distant stars and galaxies, this time lag becomes even longer. Therefore, when we observe the universe, we are essentially observing the past states of the objects we see. This is a fundamental concept in astronomy, allowing us to study objects at different points in their history. By taking into account the limitations imposed by the speed of light, astronomers can shed light on various periods in the universe's history. As we approach the speed of light, we encounter the phenomenon of time dilation, as predicted by Albert Einstein's special theory of relativity. Here are some important insights into this concept. Observer-dependent time. According to the special theory of relativity, the passage of time is dependent on the observer's motion. As an object's speed increases, its time appears to slow down relative to a stationary observer. This means that the perceived passage of time is relative to the observer's frame of reference. Approaching the speed of light. When an object approaches the speed of light, we observe that time slows down for that object. Therefore, an observer within a spacecraft moving at a significant fraction of the speed of light will experience time passing more slowly than an observer on Earth. This effect is known as time dilation or time dilatation. Practical applications. While the effects of time dilation are not apparent in our daily lives, they have practical implications in high-speed scenarios. Particle accelerators that operate at high speeds, such as those used in fundamental physics research, must account for time dilation effects. Additionally, technologies like the Global Positioning System GPS consider these relativistic effects to provide accurate positioning information. Reaching the speed of light. According to the special theory of relativity, it is impossible for an object with mass to reach or exceed the speed of light because it would require infinite energy. However, as an object approaches the speed of light, we can observe the slowing of time. The concept of time dilation as we approach the speed of light is an intriguing aspect of modern physics, shedding light on how time and space are interconnected and how they behave under extreme conditions. In conclusion, time travel, while a common concept in science fiction, remains a theoretical idea in our current scientific understanding. Concepts like time machines and time travel paradoxes continue to stimulate the imagination, but practical time travel remains a challenge based on our current knowledge of physics. Thanks for watching.